Properties of feedback circuits. Before proceeding to the analysis of feedback circuits, we study some simple examples to describe the benefits of negative feedback, as well as identify the above four elements in each case. Gain desensitization. Consider the common source stage shown in figure A, where the voltage gain is equal to Gm mod Gm1 R01. A critical drawback of this circuit is the poor definition of the gain. Both Gm1 and R01 vary with process and temperature. Now suppose the circuit is configured as in figure B, where the gate bias of M1 is set by means not to shown here. Let us calculate the overall voltage gain of the circuit at relatively low frequencies, such that C2 does not load the output node, that is V out by Vx is equal to minus Gm1 R01. Since V out minus Vx, C2x is equal to Vx minus V in C1x. We have V out by Vin equal to 1 by minus 1 by 1 plus 1 by Gm1 R01, C2 by C1 plus 1 by Gm1 R01. Here you can see the figure A, simple common source stage B, circuit of A with feedback. If Gm1 R01 is sufficiently large, the 1 by Gm1 R01 terms in the denominator can be neglected, yielding V out by Vin is equal to minus C1 by C2 compared to Gm1 R01. This gain can be controlled with much higher accuracy because it is given by the ratio of two capacitors. If C1 and C2 are made of the same material, then process and temperature variations do not change C1 by C2. The above example reveals the negative feedback provides gain desensitization, that is, the closed loop gain is much less sensitive to device parameters than the open loop gain is. Illustrated for a more general case in figure, this property can be quantified by writing y by x equal to a by 1 plus beta a, similar to 1 by beta into 1 minus 1 by beta a, where we have assumed beta a much greater than 1. We note that the closed loop gain is termed to the first order by the feedback factor beta. More importantly, if the open loop gain A varies by a factor of say 2, y by x varies by a small percentage because 1 by beta A much less than 1. Here you can see the diagram. Here you can see the figure. Simple feedback system called the loop gain. The quantity beta A plays an important role in feedback systems. We see from equation that the higher beta A is, the less sensitive y by x will be to the variations in A. From another perspective, the accuracy of the closed loop gain improves by maximizing A or beta. Note that as beta increases, the closed loop gain y by x, similar to 1 by beta, decreases, suggesting a trade-off between precision and the closed loop gain. In other words, we begin with a high gain amplifier and apply feedback to obtain a low but less sensitive closed loop gain. Another conclusion here is that the output of the feedback network is equal to x into a by 1 plus beta a approaching a as beta a becomes much greater than unity. This result agrees with the illustration in figure. The calculation of the loop gain, the calculation of the loop gain usually proceeds as follows. As illustrated in figure. We set the main input to 0, break the loop at some point, inject a test signal in the right direction, follow the signal around the loop and obtain the value that returns to the break point. The negative of the transfer function thus derived is the loop gain. Note that the loop gain is a dimensionless quantity. In figure, we have Vt beta minus 1a is equals to Vf, and hence Vf by Vt is equals to minus beta a. Similarly, as depicted in figure, for the simple feedback circuit, we can write Vt by C2 by C1 plus C2 into Gm1 R01 is equals to Vf. That is, Vf by Vt is equal to minus C2 by C1 plus C2 Gm1 R01. Note that the loading of C2 on the output is neglected here. The issue will be addressed in session. It is also interesting to identify the 4 elements of feedback in the circuit of figure B. Transistor M1 and current source I1 constitute the feed forward amplifier. Capacitor C2. Here you can see the figure computation of loop gain. Here you can see the figure computation of loop gain in a simple feedback circuit. Senses the output voltage and converts it into a current feedback signal, which is then added to the current produced in Vn through C1. Note that the output is negative even though currents through C1 and C2 are added, because the feed forward amplifier itself provides a negative gain. We should emphasize that the desensitization of gain by feedback leads to many other properties of feedback systems. Our examination of equation indicates that large variations in A affect X of Y negligibly. If BA is large, such variations can arise from different sources: process, temperature, frequency and loading. For example, if A drops at high frequencies, Y by X varies to a lesser extent and the flat bandwidth is increased. Similarly, if A decreases because the amplifier drives a heavy load, Y by X is not affected much. These concepts become cleaner below. Thank you.